F714. Draw the shear and moment diagrams for the beam. So first, we have two applied forces, but we also know we have a reaction at A. We have a reaction force and a reaction moment. So we can apply the Newton's second law to find these. Now we have a distributed force here, so we need to find its effect. We could say 8 kilonewton meters times 1.5 meters, this is a 12 kilonewton force, and then find its location is halfway there, so at 0.75 meters. But I'm going to do this the calculus way. I am going to say that the sum of forces is the reaction at A minus this force, or plus this and have the negative here, plus the integral from 0 to 1.5 meters of this W function, and then minus 6 kilonewton meters equals 0. Next, I'm going to find the sum of moments. I'm going to select moment about point A, and for this section of the text, you will always want to select the leftmost point, or the point where you define all of your x's from. It does make things a lot easier. But anyway, so we moment about that point. So there's the applied moment at A, or the reaction moment at A. The reaction force at A does not create any moment because that's the point we're rotating about. To find the total moment of this distributed force, we integrate W of x times x dx. So W of x times x dx. And this will cause a clockwise rotation, so it's negative moment. And then we have this 6 kilonewton force that's 3 meters away. Will also create negative moment. So to solve these two formulas, we find that the reaction at A is 18 kilonewtons, and the moment at A is 27 kilonewton meters. Next, we want to find the shear and moment force functions. So because we have this reaction force right here is on the leftmost part of the beam's shear function starts at the value of that reaction force. So that reaction force is 18 kilonewtons, so we know the shear at point 0 is 18 kilonewtons. Now this beam has two distinct regions, in this with the breakpoint right here. So the first region goes from x equals 0 to x equals 1.5. It has a W function of 8 kilonewton, or negative 8 kilonewton meters. So we can say that the shear at any point in that section is equal to the shear at the start, which was 18 kilonewtons, plus the integral from the starting point to our coordinate x of the W function dx. Now this W function is constant, negative 8 kilonewtons per meter dx, so the indefinite integral is negative 8 kilonewton meters x. Evaluate that from 0 to x, and we get that the shear function is 18 kilonewtons minus 8 kilonewton per meter times x for this segment. To find the next point, we need to find the shear at this point right here, which we can do so by plugging 1.5 meters into this formula, and we get the shear at this point is 6 kilonewtons. Now there is no W function right here, so we could say that the derivative of the shear function is 0 at this point, which basically means it's a constant. So in that second region, the shear function is 6 kilonewtons. All right, easy enough. Next, moment. So we do need to find the initial moment, and this is where, as I said in the lecture, this is where our sign convention, the one place that our sign convention fails us. Because the reaction moment at A was 27 kilonewton meters, that means that moment starts at negative 27 kilonewton meters. Applied reactions create negative reaction according to our sign convention. It's annoying, but it's the way that it is. So the initial moment, the starting moment, the moment at x equals 0, is negative 27 kilonewton meters. We can then find the moment function by saying moment of x is equal to the starting moment plus the integral from 0 to x of our shear function. Now our shear function is given by this formula right here, 18 kilonewtons minus 8 kilonewton per meter x. So to integrate this, we first take the indefinite integral. So 18 kilonewtons becomes 18 kilonewtons x. And 8 kilonewtons per meter to x becomes, this x becomes x squared, because this is x to the first power, becomes x to the second power, and then divide by 2, it becomes negative 4 kilonewtons per meter x squared, evaluated from 0 to x. And just to be consistent, I should put in my primes. They don't actually mean anything, they just separate what is the coordinate that is being integrated and the coordinate that is the boundary of the integration. But anyway, so we plug in x for here, so this is negative 27 kilonewton meters plus 18 kilonewton x minus 0, because that's 0, minus 4 kilonewton per meter x squared plus 0, because again this is 0. So this is the moment function for the first half of the beam. Last segment, we need to find the moment in this piece of the beam. So to do so, we need to start by finding the moment at the boundary between the two sections. That point is 1.5 meters, so we plug in 1.5 meters for x in this formula, and we get that the moment at that point is negative 9 kilonewton meters. We then say that the moment at any point x is equal to the moment of that initial point plus the integral from 1.5 meters to x of our shear function there, which was, again, positive 6 kilonewtons dx. 6 kilonewtons, the indefinite integral is 6 kilonewtons x. Plug in our bounds from 1.5 meters to x. We get here, combining like terms, we get that the moment function for this segment of the beam is negative 18 kilonewton meters plus 6 kilonewtons x. So to draw this, for the first segment of the beam, V of x start is 18 kilonewtons minus 8 kilonewtons per meter x. This is a linear graph, so we could go ahead and draw a straight line. We know that at x equals 0, it's 18 kilonewtons, and at x equals 1.5 meters, it's 6 kilonewtons. So this is a straight line going from this point to this point. And then for the second segment, it's flat. V of x is constant. So we could draw a V of x graph that looks like this. Now for the moment graph, there are two ways we can figure the moment of this. First is by looking directly at the moment functions that we calculated. This one is a quadratic equation, which means that we're going to have a section of a parabola. And this one is linear, which means we're going to have a straight line connecting the first point and the value of the second point, which you would get if you plugged in 3 meters into here, which is 0. Now, doing it like this, it is kind of hard to draw a graph like that, although you could use a spreadsheet program and plug in the function of m of x in there and draw it. However, there is a way you can kind of freehand, or at least use this to make sure you have the right looking answer. And that is to remember that v of x is the derivative of m of x. So how you see, for this second segment, moment should be moving upward at with a constant slope because v of x is constant. And if we look at here, we see yes, for this segment of the graph, it's constantly sloping upward. For this segment of the graph, because v is always greater than 0, moment will be will always have a positive slope. So it will always be positively sloping upward here. But because v is decreasing, the slope will decrease. And at the point between the two segments, the slope should smoothly go into this flat segment right here. So you get a little bit of quadratic curving here, and then a flat segment right here.